This is ST536, Fundamentals of Information Technology. I'm Rob Hepler. There's my contact information. Today we're going to talk about storage. Talked about getting data and stuff into the computer. We've talked about processing it, input, process, output, IPO. And that's really nice that a computer can do those things for us. We can have things go in and we can have things come out and we can enjoy them. Of course, without this last component, concept, storage, it really isn't very useful, a computer. If we had to load everything we wanted to operate on or see or view every time we wanted to use a computer, it's very tiresome. In fact, the first PCs were like that. You had to load everything you needed every time you turned it on. It was a nuisance, but that's the way they worked. It was too expensive to include storage. So over time, we figured out ways to make storage smaller, like everything else, more storage, cheaper, and better technology. So the idea is all this analog stuff out here in our world has to be converted to something digital, which is then stored and retrieved as we tell the system, the computer, to do that. Remember when we talked about the early days of computing concepts on John von Neumann in a different lecture, and those people, one of the things they held to was this idea that everything had to be stored the same. Instructions, data, information, programs, they all had to be stored in the same format, essentially. And that's what we have today. Everything we use on the computer is stored in the same format using what we call a character set. We had to decide on what is an E, the letter E. And remember, the shape of the E is just kind of arbitrary. It doesn't mean anything inherently. It means something because we agree to it, what it means. And the pronunciation, it's arbitrary, but we all agree that the pronunciation for that symbol is E. Well, the same thing goes on here. We had to devise a character set, and we all had to agree on it. If we didn't agree on it, if every computer had its own character set, every manufacturer, every software developer had its own character set, we would not have the explosion of information we have now. So briefly, let's go over a couple of concepts here. Storage holds data. That's the stuff we want to keep, the stuff we create, really. And there's also system data that the computer keeps for its own benefit, which we don't really care about because it's happening in the background. Instructions. Remember, when you turn a computer off, everything goes away, except storage. So the operating system, the programs, have to be loaded when you turn the power on. And finally, information, which of course is data that has been processed in some way. The screen I'm looking at, this PowerPoint you're looking at, is information. It's stored on a hard disk in zeros and ones. And we'll talk about how that happens in a minute. A storage medium is the material that's stored, that the data is stored on, and I would modify that a little bit. It's not necessary. There is physical material somewhere. Storage has to be physical on some level, because if you lose power, the only thing that remains is physical storage. So somewhere, somehow, there has to be physical storage for everything you're doing. When you go to a web page, that web page is being pulled from a physical storage somewhere and sent to you via the internet. Okay, but the other thing I want you to think about is the location of that physical material is starting to not matter anymore. It mattered a lot up till recently, and now we're starting to get to the point where we can store stuff up in a cloud, as it's called. Which means, again, as technology advances, distance means less and less and less, means nothing. And we'll talk about that, but just keep that in mind. Storage medium. Storage needs a medium. It needs to be able to pull something from the time it's turned off to the next time. Here we have some different storage devices. Here's the hard disk. You all should know what that is by now. What else? Miniature hard disk. Solid state drive. That's flash memory, and we'll talk about that. And then there's memory cards. You've seen these. Your camera has these things, and maybe your MP3 player has those. But here's an interesting one. Talk about physical, microfilm. Well, once upon a time, that was a great use of physical storage because it lasts a long time and it's very cheap, and it doesn't take up disk space. That was important when disk space was very expensive. I did a project at the University of New Mexico years ago as a consultant where we had to remove data from the registrar's history database in order to free up enough information for current information. And what was happening, because of the lack of space, registration got very slow. So we needed to streamline the database. And these were things you did when processors were slow and expensive and data was expensive. So what we did actually is took the oldest information and created a data file which we sent to a service, and they created a microfiche. Microfilm. Microfiche is the same thing, except there's little cards you use instead of these rolls of film. And then in the database online, we put an address, what row of microfiche and where on that row you could find the information. So when you pull up a student's records, you'd see the current stuff. You'd see the last 5 years, or maybe more. I don't remember how far back we went. But prior to this, whatever cutoff we chose, you had to go to microfilm. And it worked fine, because you didn't get many requests for those, of course. And as a result, registration went up. Today, you probably wouldn't even bother with that. You would just add more storage because it's become so cheap. And you can buy services to store your information. Okay, so that's why it's in there. I would say its days are numbered. So you're going to see less of that, because now instead of taking a hard copy and turning it into microfilm, just turn it into digits on a computer. Well, this is a storage device. Your credit card, your smart card. Europe uses a lot of smart cards, as I mentioned somewhere else, and that stores the data for you. Optical disc, the CDs, DVDs, Blu-ray, you all have used those or know what they are. I haven't used CDs in years, and I have some old DVDs I watch once in a while, but most of what I watch, if I rent something on disc, it's Blu disc. And we'll talk about that. Cloud storage, important concept. It's changing the way we do things. And we'll talk about all these things. Before we get into that, though, I wanted to talk about how we represent data, and then we'll go through the kind of hardware side of things. Originally, when computers were invented, as we know, RAM was expensive. In fact, Bill Gates once said he couldn't imagine we'd need any more than 480 kilobytes. Kilobytes, that's 480,000 bytes. Now, of course, we're talking about 4 gigabytes of RAM or more. So he was off a little bit. But the point is, he said that because it was expensive. Memory was expensive, storage was expensive. So we had to figure out a way to store things in a common kind of setup. And because of that, because storage is expensive, we created a code set, character set, if you will, called the American Standard Code for Information Interchange, or ASCII. ASCII code still floats around, but and it was used for decades, and it allowed us to store things. 8 bits is what most chips were, the architecture, because again, it was expensive. We now have 64-bit processors instead of 8, much faster, data moves faster, processing's faster. But of course 8 bits was all we had in those days, so that's what the code had to use. And because of that, what we created was an English character set, and the whole world had to use it for decades. It worked for America, and America was kind of the engine for the economic growth after World War II. We were it, pretty much, for obvious reasons, but because of that, we just developed a character set, and because we were producing the computers and we were using the computers, we were writing the software for the computers, we just did that because it made sense. You could get a level, a threshold of production that allowed the price of computers to go down, and then the rest of the world started using our computers. And to use them, they had to use our code set, ASCII. The UN actually adopted that as well at some point. Of course, what that means if you're a Japanese is you have to learn English, at least to operate the software and the operating system. And remember, the Japanese have a whole completely different character set, as do the Russians, you know, Eastern Europeans, Indians, you know, Chinese. They all have different character sets than we do. In fact, in our own country, the Cherokee alphabet was developed by Tecumseh, I think his name was, a chief that wanted the Cherokee to integrate into American culture, and so he developed an alphabet. Well, they have characters in their alphabet for pronunciations we don't have. German has some things like the umlaut. They're two dots over a vowel, and you pronounce it a little differently. Well, that wasn't included in the ASCII set. In fact, even today, Germany now adds another E or another vowel where there used to be an umlaut in some cases because of that. So even their spelling has changed, and the official spelling changed because of that. So it had a big cultural effect. The Japanese, for instance, lagged behind us by years in automating their offices because their documents were all in their Chinese character set. It isn't the same character set, but it's based on the Chinese character set. So because of that, they couldn't use Office as well as we could, and they didn't really have the motivation we did to store documents and so forth. They also had a cultural bias to keeping hard copy, and in fact, they teach writing like 3 hours a day in schools because it's such an inherent part of their culture that you should know how to write those characters well. It has a lot to do with how people think of you. So it was also part of their culture, but the software and computers also lagged them behind. It made it difficult to work in other language. But the standard helped us move ahead. When the chips started getting better, memory got cheaper, we developed something called the Unicode. And this is the UN adapted this, and it's pretty much what we use now in all computers. And there's variations of the Unicode, there's extensions, there's a lot of different things because it's possible to do that, and we'll talk about that in a minute. It uses 16 bits, or double the bits, that ASCII used. By the way, you can work out 8 bits, 2 to the power of 8 is 256. And since computers start counting at 0, the ASCII code set goes 0 to 255. Well, with 16 bits, that's what you get, over 65,000 characters. So we went from 256 characters to over 65,000 characters. Now all of a sudden, we just need to develop a character set for anything. In fact, I don't believe to this point we've used all the 65,000 plus possibilities. We've used a lot of them, but not all of them. Let me bring this up here. Excuse me. Here is an ASCII code set, character set, code set. And this column, let me roll this down a little there. This column is the decimal, that's our numbering system, 0 through 9, number. And the character itself is here. So quite simply, for the character A, capital A, by the way, the ASCII code is 65. And of course, you have to express that in base 2. So that's something to think about. So you've got bits on or off in what it would be 65. Just to give you an example of that, let's when we communicated a lot over phone lines, and we still use these things in the background, you had to know about start of text characters and things, and that decimal ASCII code is 2. Well, to express the number 2 in binary, and we have 8 bits, there's 8 bits, and that's what the chips had in those days, 8 bits. And of course, we had to turn these on and off. That's all we could have is on or off. And of course, obviously, if we turn this one on, the rest off, so those would be zeros, and this would be a 1. That would be the number 1, obviously. Okay? So the number 1, if we go back to our chart here, is actually the null. I'm sorry, 0 is null. And believe it or not, you need that. That means nothing. But you need the space there, and you don't want it to tell it the space. So that's what null is. But the 1 is start of heading. Headers are used in communications. We'll talk about that when we talk about networking. But if we wanted to do 2, start of text, well, the way you do 2 in binary, you would add 1 to 1, obviously, and that would be a 2, wouldn't it? But we can't write 2 in base 2, so we have to write a 0 and carry the 1. That's how you do it. So this is the binary representation. There's the 8 bits. 6 zeros, a 1, and a 0. That equals 2 in decimal. You get the idea? How would you do 3? Well, 3 would be 11. Those are my funny ones, by the way. How would you do 4? Well, we can't write a 2. We add 1 to this. This becomes 0, carry the 1. This would be 2, so it becomes 0, carry the 1. That's 4, and so forth. So the computer, using the ASCII code set and the binary numbering system, stores all those characters that we need it to store. Let's see what 3 and 4 are. Let's pop back over here. 3 is the end of text. 4 is the end of transmission. When you send communications, there's all this stuff that surrounds the message itself, which is sent by the sender, received by the receiver, and interpreted. And we'll talk about it later. And you can see some of these things come from typewriters, form, feed. You get the idea. In fact, there's only 127 of the, there's only part of the code set here. It goes up to 255. You can find those charts elsewhere. So that's how that works. This is how binary works. Number 1, this is 2, this is 3, and this is 4. As you can see, you start using up numbers pretty quickly. But that's how it works. And of course, a 0 is off, and a 1 is on. And sometimes magnetically, that would be north and south. You just make a decision which is north and which is south. As long as there's 2 different charges, if you will. Okay, so that's the ASCII chart, and computers use those. This is real quick. I'm not going to talk much about this. This is the ASCII, or IPSIDIC, I'm sorry. Right here, IPSIDIC. And IBM created IPSIDIC. I don't remember what it stands for, but and it's still used on tapes sometimes, but it's just the same thing as ASCII. It's just a different code set. Okay. And it didn't catch on. IBM tried to bully people in those days and force them to do things, much like Microsoft did for a long time. But ASCII became the standard rather than IPSIDIC. It's simpler. But you might see that around. And I just want to mention it because to tell you that there can be other character sets. It's just that the standard ones are the ones we need to know about. Now, I mentioned Unicode. And this is Unicode. And keep in mind that Unicode has 16 bits. So if you have an 8-bit computer, you got to use 2 bits for each character. So you can see you've just halved your storage. This only worked because memory got cheaper, storage got cheaper, okay? But Unicode, of course, still uses 0s and 1s. It's just got 16 of them. So it has more options. So let's take a look at this. The basic Latin would be our English, if you will. French, German, I suppose. Taking a while to come up here. And it's the same idea, it's just different codes, and there's over 64,000 of them. I'm just trying to get the idea. I'm not going to go through these codes, but now look at what we've got here. It's just unbelievable. Phonetic extensions. There's extended Latin, which would include German, French, those kinds of things. Spanish has a character that hangs on the end of certain letters. I don't even know where some of these things are spoken. Gurmukhi. But it's all here. It's inclusive. And once the UN saw this, of course, they accepted it. And now this is how computers ship with Unicode, of course. let's just take a look at one of these. Katakana is the Japanese character set. There it is. Now you can display these because you have a code for them. It's not that the monitors couldn't display these codes. Of course they could. Those are just pixels, remember. Those are just dots on the monitor. Or print them. It's just a print head. We didn't have a code for them. Now we have a code. The Japanese can now save their language in Microsoft Office. What else? I mentioned Cherokee. Yeah, here it is. Here's the Cherokee alphabet. This was developed by a guy by the name of Tecumseh, I think. If I'm wrong, let me know. Anyhow, he developed this because there's some pronunciations in Cherokee which don't translate into the Latinate English we use. And you can see here's the charts and the code. So the point is, there's a code for everything now. It's inclusive. And to convert from one character set to another, it's a little simpler now because you can add or subtract numbers and probably translate it closely anyways. But now there are you can control things. And you could see that you could develop a translation a little easier of the characters, not the language itself. That's a whole other thing. Of the characters into a more recognizable form just by changing the codes. So that's what we have, and we still haven't filled up all the Unicode slots. There's still some that are empty. I mean, there's some stuff in here just like mathematical symbols. There's a code for these as well. You know, electrical symbols. So this was a great leap forward, all predicated on the fact that chips had more bits, memory has more bits, becomes cheaper, we can do this. Remember, from 8 to 16, you just cut your storage in half because you need twice the amount of storage for one character. You get the idea. You get the concept. Okay. So that's how we'll represent everything. Anything I talk about, any storage is done in Unicode or ASCII or occasionally maybe IPSID. You get the idea. Mostly Unicode. So whatever I talk about, when we talk about storage, it's all stored that way. And remember, let's just take a look at this for a second. We talked about this IPO, input, processing, output, and there's also, on this side of things, storage. The processor accesses storage, processes it, and then sends it out, actually. And the input can come through the processor and then go to storage, processed and go to storage. So what happens, for instance, you press the letter E. Well, that tells the hardware to send a special code to the processor. Processor says, I know that. That's the ASCII. I'm going to say ASCII. It's just what I'm used to. It's really probably Unicode. Number so-and-so. So I know that's what to generate and to store that code. When I retrieve it and go to output, that's the symbol I want to portray. So there's a code that's stored, and remember, everything goes through RAM. So if you type on the keyboard, it's really going into RAM. But if you're done with your Word document, it goes to storage through the processor. And all that's in your Word document is zeros and ones. Remember that. There's nothing else in there because there's nothing else a computer can store. It's just storing zeros and ones, and they represent all the formatting, all the characters, all the bold numbers, colors of your fonts, different fonts. There's codes in there telling it changes to this one, and so forth and so on. Okay? So that's what's going on. The processor is either writing in ASCII or Unicode or reading the Unicode. And once it has it in RAM, it can process it. And when it outputs it, it has to put it in some kind of representative visual signal for us, or audio signal, it's music, or video. And the input, of course, comes from the waves somehow, and it has to be converted to digits, and it's all stored in zeros and one. Now, when we start talking about the capacity for storage, that's just a term we're going to go through, a few terms here. Here's a chart. I'm not going to go through it, but you might have heard of some of these. Everybody knows about terabytes even now. A few years ago, gigabyte was unheard of. Now we're talking terabytes now. Petabyte, exabyte, zettabyte, yada. Yadabyte. Yada, 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 yada. That's 2 to the 80th. 1 septillion it's called, and so forth. You see the stories there. The only thing I want you to notice here for sure is that it's not really 1,000, even though we call it a kilo is, Latin, Greek, I don't know. One or the other for 1,000. Mega is a million and so forth. So as you can see, 2 to the 10th is 1,024. So we're always a little more than the designation. It's more than a million, it's more than a billion, it's more than a trillion, and so forth. And that adds up as we go down here. But we'd still talk about it as this column here just to keep things simple. Kilobyte is actually 1,024 bytes. So a storage device, which is a disk drive, you all know about disk drives for one thing, records and retrieves items to and from storage. Okay. Reading is pulling the ASCII code off the storage, transferring it to RAM, doing something to it, and then sending it out. Writing is transferring items from memory, from RAM, back to the hard physical disk. Okay? Reading is pulling it from the disk. Writing is putting it on the disk. It's that simple. Makes sense. Access time. Well, every physical device has some amount of time it takes to find where the data is stored and then to retrieve it and bring it back to you. So the access time is the amount of time it takes the device to locate and then deliver it. Locate, retrieve, and deliver it. And of course, RAM is fastest of all because it runs the speed of light. As we get down here, these are very physical devices. They actually have moving parts. Well, an optical disc does, a tape does, a hard disk does. When you start talking about moving devices, that's just like a snail's pace when you're talking about the speed of light. So there's really no comparison between RAM and any of these devices. RAM has to wait for hard disks. RAM has to wait for USB flash drives. They're quick, these are quick flash drives, as we'll find out. But the others are physical. Flash drives are not so physical. So optical discs and tape are physical, and they have moving parts, which makes them very slow. Access time is how much time it takes to find something. And we're going to look at a disk here. And this is, of course, a hard disk. I hope you've seen those. This is the arm. And on that arm is a head. And that head reads or writes onto the surfaces, really, of this platter. So it has one or more inflexible circular platters, and they use magnetic particles to store the data, instructions, and information. So it's magnetizing a bit, or turning the magnetism off. Off is a 0, magnetized is a 1. North is 0, south is 1. Don't know how that goes, but it doesn't matter as long as there's 2. All right, so let's take a little closer look at the disk. And this is a platter, and the disk has concentric rings. I can't draw circles, but they're perfectly round, and there's a bunch of rings on a disk drive. Although we talk about this as if it were a phonograph record, and it's not, because these disks, the rings, if you will, are independent from each other. There's no track from one ring to the next, like there is in a phonograph record. And I'll show you an example of how a phonograph record works later, but because I know most of you don't know what I'm talking about. So these rings are here, and we store, as you can see here, north, south, they're talking about plus, minus, whatever you want to call it, on, off. And on here, we split these rings into sections that we call bytes. 8 bits is a byte, although you can have 64-bit bytes and so forth. But for now, I'm going to talk about 8-bit bytes. So 1 byte is 1 character in the ASCII. Okay? 16 bits is a character in Unicode. Now those bits are turned on and off here on the rings. So the physical disk of the platter, as it's called, only can have so many rings, and then you have to decide how to split that ring into segments to store data on those rings. What they're talking about here is it's, newer technology allows you to use the surface of the disk and write down rather than across the disk. And that's about all I want to say about that. Characteristics, capacity, how much can it hold? Terabyte, megabyte, gigabyte, what is it? Platters. There's also the read-write heads, and those are the things that don't touch the disk ever. A disk crash is when your disk head hits the disk somehow. If you're operating your disk and you drop your computer, that disk is probably going to crash. If it crashes, you're done. You cannot retrieve anything from that disk. So that's the concept. It's a little head. We'll look at side views of these. A cylinder is a abstract concept, and we'll talk about it in a minute. It's essentially if you have more than 1 platter, you take the 8th ring in each platter. Think of a soup can, a cylinder. So the 8th ring on all the platters is logically grouped together, and it makes it quicker, and I'll show you why. Sectors and tracks. Well, the tracks are what I'm calling the rings. Those are the tracks on the disk. And the revolutions per minute, RPM. Why is that important? Well, the faster the disk moves, rotates, the quicker, the less the access time is, or the quicker you can retrieve the data. Transfer rate is how fast it moves along the buses. We talked about a bus. How fast it moves along the channels to move the data. And access time is how long it takes to get all of that and give you the information. Your disk normally for most of us comes formatted. But let me just show you this real quick. I lost, 1 second. There it is. Okay, if I go look at my computer, right-click on the C drive, go down to Properties, there's that picture. This is for my disk here. 111 gigabytes is how much space I've used, and I have 343 remaining. Here's the total capacity, as we talked about, 489 blah, blah, blah bytes, which we call 455 gigabytes. I just wanted to see how that works. The file system here is NTFS. Don't worry about that. We're going to talk briefly about that. And over here, I went to Tools. And this is where you can defragment the disk. And we'll talk about that. I just wanted to show that to you in case you want to do that on your disk. Okay. You normally don't get the full capacity. That's why they say advertised capacity here. Because there's always something that takes up a little overhead, as it's called. All right. There's a circuit board controls the movement of the head. This is the head here. That head moves across the disks, and it seeks out a certain track or ring, concentric ring or track. And it goes to that track, and then it looks for a specific sector, it's called, or a specific location on that circle, on that track, on that ring. So it has to sit there on that ring and wait until the address it's looking for comes around, because the disk is constantly rotating, but the head only goes in and out, in and out. The head only goes this way, the disk goes this way. So the head goes to the right track and waits till it reads the proper sector, and then it retrieves the information from there, or writes it, depending on what it's doing. And then it moves those zeros and ones along a transport, electronically, and across that and then back out the disk through some cables here. Okay? That's essentially how it works. A better diagram here, I think. So you've got more than one platter on most disks. That gives you a higher capacity. and you've got more than one arm. So you've got this particular disk on the top here, the very top one. You can read and write on the top and the bottom. And I know that because there's two heads here. There's a head reading this side, which would be this one. There's a head reading this side, which would be this one. And then the same thing here. So you're actually utilizing both sides of those platters. Okay? Now, that's why we talk about this concept of the cylinder. If we can move all four of these heads to the same ring, we can retrieve something on that ring all at once. It's much quicker than having each of those heads go to a different track on a different part of the platter, and it just starts jerking all around. So what we want it to do is all move at once, go to one ring, and retrieve a cylinder and bring it back. And if this is difficult, to follow, just think of the idea that we want to move these arms as little as possible. They're what's slowing us down, and the speed of the rotation, of course. But those arms are physically have to move, and they're also what wears out. One of the things that wears out on a hard disk, the arms moving constantly. They're moving so fast you can barely see them. On mainframes, you can hear these arms moving around, the disks rumble, all kinds of things go on. So if we can get them to move all at once to one location, retrieve all that data and put it together in one string, rather than store it all over the disk, it's more efficient. Let me go back over here to our notebook. So our disk here, if we had, the letter E, I don't know what the code is, but, and remember we've got these rings here. And notice the rings, of course, get smaller, obviously. And the processor tells us we need to store some 0 and 1 bit. I don't know what the code is, forgive me. But some 8-bit pattern, on-off pattern. Well, that gets sent along a channel to the ARM. And then the ARM finds a place on the disk that's not being used by anything else and stores that E. And then if it's somebody's name, Ed, what you want to do, if you store the E here, you'd like to store the D here, right next to it, when you're writing it. That way when you read it, you can pull the E and the D off right after. You don't have to move the head at all. You just keep reading on that track. I hope that makes sense. And then if it's Edward, you'd want the W, A, R, D, and that would be the ASCII or Unicode for those characters, stored right there on the same track, one after another, so the head moves to here, the disk runs this way, the head just picks up all of those codes, one after another without even moving, and sends it back to the RAM. The processor reviews it and says, I know what that is, and displays these characters on the monitor for you. That's the best thing that could happen. Well, when you get the disk, it's pretty much fresh with a lot of free space on it. And as you use it, it starts getting chopped up. Because you may have, when you got it, stored one big file here. And then another file here, and another file here. So this is 1, 2, 3. This is a smaller file, in-between file. And then in the meantime, you needed to store something. Well, the only free space we've got here is here, 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 here. That's the only free space we have left. Well, if I want to store something bigger than this, let's say, the fourth location. Actually, this isn't free space. I'm sorry. This is 1 from here to here. Okay. So 1 runs from here to here, from here to here. Okay. So you've got these 3 areas, and I've got something that's bigger than this, let's say, than this one over here. So to store that, I need to put part of it here, so this would be 4A stored here, and 4B stored here. So although I think of it as a human being as one string of data, the computer has to store it in 2, and maybe even 3. Okay? And now what happens if you delete 2, you get a little more free space here. And as you do this, as you add and delete things, it becomes chopped up. And what you can do is run a utility for that. And if we go back over here, it's one of the things I was talking about here. If I go to Computer, right-click on the disk drive, Properties, Tools, I can defragment the disk. So what happens is it gets fragmented. Okay? So that means that all your data is chopped up into different locations, and what happens to pull that data off the disk, the ARM has to go crazy, move all over the disk drive, pick up the bits and pieces, put them back in the right order, and then send them onto RAM. Very slow process. Remember, any physical movement is slower than heck compared to the speed of light. And that's called defragmentation, or it's called fragmented, and then the process is defragment. Okay? So that's what that's called, and that's how you do that. That's an important thing. If your disk gets really slow, if it's very fragmented, it slows it down, because to retrieve or write data, it has to write in not just one location, but many. And what defrag does is pull all the data out and try to put it back in just big chunks. Okay? If that's confusing, let me know in the forum, and we'll talk about it or do a little research. Just to show you how close and how small the tolerances are, that's what this chart is showing you. The read-write head of the disk is here. And here's a human hair. This is the distance. This is from the platter. So human hair is just outrageously huge. Piece of dust, you get the idea. When people smoked a lot at work, that was an issue because the smoke particles would get into your disk drive and destroy things. So if the head runs into one of these particles, it's going to bounce, it's going to actually strike the platter and destroy part of the tracks. So it's something to think about. Most disks are sealed pretty well these days. You don't have to worry too much about that. In order, everything, we've talked about this, everything in computers is a trade-off to speed things up. RAM, or memory, is the quickest form there is of storage. And so we have something called a cache. Cache is used all over the place, many different locations on the computer to speed it up. We talked about cache in the system unit on the chip. We cache certain instructions and so forth. But disk drives now have memory on them, or RAM, if you will. We don't call it RAM, but it's the same idea. And the cache stores the most often, most recently used data, instructions, whatever it is. It stores it there. It pulls it off the disk and stores it here. When the processor, asks for data, it first looks here. And then it pulls the information from there if it can. If it doesn't find it there, it goes to the disk drive. Okay? That's just one way to make it faster. You can get the information from here. That's flash. That's RAM fast. So if it's something you use all the time, it's probably going to stay here. Or something you used recently, it's quicker. It's just a way to speed things up. If it has to go to the disk, that's okay, but it's a lot slower. And of course, how much you have here in cache. If you could think about it, if you could cache the whole disk drive, of course, you wouldn't need a disk drive. You could just use the cache. But of course, you can't. It's too expensive. So, but the stuff you use most often, most frequently, can be stored there. Now, to the processor and the programs, it looks like it pulled it from disk. Doesn't matter. And it processes. Just a way to speed things up. Disk caching. I don't talk much about RAID, but it's a way to store data redundantly. And there's, gosh, I don't know how many different RAID 0, which is essentially every time you write a byte, you write it twice on 2 different disk drives. So it's a backup, if you will. It's called mirroring. I think that's RAID 0. So everything you store is stored twice, and you need double the storage. But what that means is if your primary disk goes down, you have another one that's an exact copy of it that can just fire up without pause. Your processing can keep going, and then you can pull out the bad disk, repair it, put it back in, and RAID is smart enough now to make that disk look like the mirrored copy. So it'll start copying the data onto the disk after you plug it back in, and then they'll be synced up again, a mirror copy of each other. And then you'll just keep processing that way. So the idea of RAID is it's built-in backup. There are other ways to do that. You can put a digit that tells you if you lose one bit, you know what that bit is if you add up the other bits. I'm not going to go into it any more than that. Network attack storage allows people, you all use this, to access storage, shared storage. The concept is it's cheaper to buy one big storage unit than to have each person have a lot of storage. It's also simpler in some ways. You can just back up this instead of everybody backing up their hard drives. For secure sites, all you need to do is lock this up and you're secure, or you're more secure than you would be if you had data distributed all over the place. Lots of reasons for doing that. Usually it's efficiency, speed, security. A NAS. All right, hard disks. Well, we know the built-in hard disk is there. Many of us don't see them often, but we know what they look like. But there's also this concept of an external hard drive. And I'm getting away from all of this stuff, and we'll talk about why in a little bit. External hard drive is just a hard drive that plugs in normally your USB drive. Plug it in, you're ready to go. And it's getting so cheap, you can get a terabyte of data for, I think, around 30 bucks or something. It's just incredibly cheap. So it's a way for you to back up things or to move things around. It's a nice way to go. Removable hard disk, you don't see many of these. What you have is a device here. And then this thing slides in and out like a CD, except it's a hard disk. Now that's used at secure locations where they'll lock up, and then they'll use external drives too, where they'll lock up these things, the removable disk, in the evening when you go home because it's secured, it's full of secure documents. So that removable disk can be put somewhere safely, and it's checked out in the morning, checked in at night, and so forth. Just a secure process. Other than that, of course, it's another way to, you can take your storage off-site, but it's, you know, why wouldn't you just do that? The technology's kind of removed beyond removable hard disk, except for specific reasons like security. And then there's these other smaller hard disks. The iPod, the classic, for instance, has a hard disk in it. I think it looks like this. And it stores your music on the hard disk. And that allows it to store more than the newer iPods, not classic, because they store it on what we call solid state or flash memory. And we'll talk about that in a second. But that's a hard disk in that iPad, which is pretty amazing because you bang it around, you drop it while it's reading it. And of course, it doesn't read the disk, it caches most of your music. That's why if you've ever skipped ahead, I don't know, 10 tracks, sometimes it takes a long time because it actually plays it from the cache. And you may have 10 tracks in the cache. If you skip ahead too many, it's got to reload the cache and then start playing at that point. So that's a hard disk too, internal one. So I'm not going to talk about this much except to show you pictures here. Types of storage. Most of us don't deal with this, but real quickly, this is SATA cables. And they're used internally in your computer to connect the disk drives to the motherboard and so forth and so on. Serial Advanced Technology Attachment, SATA. These are just different ways to access disk drives. And the disk drives themselves, the processing, the speed at which they send and retrieve things is dependent on the architecture you use here. Enhanced Integrated Drive Electronics. This is also SATA. This is EIDE. You've probably seen plugs like that. This is, and each of these is a wire. You'll see that on buses. And that's inside your computer, the bus that carries the data from your processor to your motherboard and so forth. And this is also EIDE. This would be how it plugs in here. This is called a SCSI. That's what it's called, SCSI. So this is 3, this is 2, and this is 2. Small computer system interface, and their plugs and cables are pretty distinct. They're real thick, and they're used for short-term things. I learned the hard way. It's something I never thought of until it happened. When we were setting up our print facility for Kinko's just before the Olympics, so we could get the print shop in the all our Kinko's in Salt Lake and surrounding area. I had to get it to work, and we had a vendor helping us. But I hooked up all the printers, got everything working, and everything was fine, except once in a while. And what you do with SCSI, real quick, you do, if these are printers or disk drives, it doesn't matter, printer or disk, and you do what's called a daisy chain. So the computer is here, you have a SCSI cable here, then you go here, then you go here. So that's called a daisy chain. And each of these printers had a different function, size mainly. The paper was a different size because, you know, we're worried about labor. We didn't want to have to change paper. And the type of technology we were using, and it doesn't matter. So each of these had a different function, and the computer would send it out, and the address would tell the processes which one to go to. Well, the total for this cable 1, 2, 3, the total of those 3 cables couldn't be more than 12 feet. SCSI doesn't work if the total of all its cables is longer than 12 feet. Who'd have thunk it? Has to do with the amount of electricity it sends down the line and the impedance. So as I started setting these up, often the third one would work and then not work and work, and that's because I had cables that were too long. We had to bring the printers back together a little bit, shorten the cables, work beautifully. That's the kind of thing you don't think about. Doesn't really make sense that that would happen that way. This you'll see often, and this is using SCSI. These are all connected, you know, there's more than one serial SCSI, so there's more than one SCSI controller or hardware, and they're connected this way, so you can have all these disk drives connected very quickly, and then you'll have a one controller coming out. It's just a way to have an array, if you will, of data storage. Don't remember much about that. I just want you to be aware there's different ways to do things. And if somebody asks you about it, you might have heard about it. Flash memory, we all know that term now. The memory that stays, it's non-volatile, as is the hard disk. It's non-volatile because it stays when the power's off. This is a flash memory. You can't see this. It's a little USB drive. That's how I brought my PowerPoint over here. Flash memory, they're solid state, which means they keep the data after the power. Well, it really has no power, because the storage is done in there chemically in many cases, and magnetically it could be. Well, what's starting to happen, and you're seeing this more and more, there's a Apple laptop that doesn't have a physical rotating hard drive. It doesn't have any moving parts for storage. It's just using solid state or SSD. No disk. It's all the same type of memory that's in this USB drive. And of course, that's great because there's no head, there's no arm, there's no motor running a disk and revolving the disk. So all those things are good. And here's some other advantages. It's faster. It has to be faster. There's no physical movement. Faster transfer rate, so it's moving it. The access time, if you will, is less. There's almost no heat because the heat comes from the motor turning the disk. If you think about it, moving the arm. Power, nothing. You just have a little bit of power to go out there and retrieve the bits. No moving parts. You get the idea. It lasts a heck of a lot longer. The downside is this. Right now, to get the same amount of storage, I think on this computer I had 0.5 terabyte or 500 gig, something like that. Well, to get that much in flash memory would be incredibly expensive. The cost of my laptop would go through the roof. So one of the compromises Dell does, they keep the operating system or OS on the SSD, and you can also load some of your own programs on there if you use a lot like Word, you know, MS Office, whatever it is. And then you also have a physical disk, hard disk, to store your data. The concept here is it boots faster, your programs load quicker, that kind of thing, because it's coming off of flash. but it's not as expensive if you had a complete flash memory storage system. And this is a solid-state disk drive. That's all it is chips. Okay, nothing, magical about it. It's just replacing a physical drive with arms and rotation with what's essentially non-volatile storage. And there's some flash memory. And I'm not going to go through these, but here's a list of all the terms. If you want to look at this, you'll have access to this. You've seen some of these. Your phone probably takes something like this, a micro. It's a micro SD. I don't even know what's on here. But you can open your phone and add one that's bigger. I've done that with my phone. The point is it's non-volatile. It's fast. No power. Or little power, little heat. Not much here. They're just showing you that there's actually a controller in this device. When you slip your photo card in there, and it just reads it. Not much to talk about there. USB, here's the memory. Express card module. It's kind of an interesting thing. You're seeing less of this, of course, unless you have specific functions for your computer. All the older laptops we have here in the office, I still have in the closet, didn't come with, for instance, wireless cards. So I could slip an express card in the express card module that had a wireless processor on it. And all of a sudden I had a wireless laptop. Could access the wireless network. You can also do that and get Bluetooth. But this is becoming less necessary unless you have specific technical reasons for doing it, special applications or something. But in most of this, what we can use is the same idea, but we can get something that plugs into the USB port. And if you don't have wireless, you can get something that plugs into USB, and it acts like wireless or Bluetooth. So these are kind of, except for specific applications, being phased out. One of the things I want to talk about for a second is this idea of the disk. There's something called the file allocation table, and that's what I'm going to call it. There's other ways to do this, but I think this is the best way to talk about it. How does the computer know where you stored your information on all these rings and all these locations? Well, it actually has a table of contents, or TOC. When you create a file, it puts an entry in here. Let's say I called the file resume. Well, in this table, there's an entry that says resume. .doc. When I tell Word I want my resume, it tells the operating system, and it goes into this table of contents, because it can't search the whole disk. That would be incredibly slow to find my file. And right next to this is an address that tells it what ring or what track, and then what part on that track to go to, sends that to the ARM, and the ARM goes right to that track, waits till your location comes around, and reads it. So this, the file allocation table, and there's other ways to do it, and there's other terms, but the idea of the table of contents is how the computer keeps track of your files and where they're located. Now, if this file is fragmented, at the end of this storage will be another address. It says go from here to here. And then if this one has to go more, there's another address there which might go to this ring, and so forth. So address, ring, sector, track, sector, cylinder, those things are restored as an address. Okay? I just wanted to get that concept of, it doesn't search the disk, it goes to the table of contents, finds your file, and says, it's on ring 6, sector 9 or something. Okay, I don't want to get into the details of it, just the concept for you. We're going to talk about databases, and that'll make a difference then. The cloud storage, simply put, everything I've talked about is true. Right now I use several services, but Amazon is where all my music is stored. And I have my computer, my PC over here, and I have all my music on here. And I signed up for a service called Amazon Prime, about $70 a year, but I get free shipping and a lot of neat things. One of the things I get is storage. for my music. And you can also get storage for everything. I just have the music aspect of it. So Amazon has software that went through my computer, found all my music, and put it up here on a disk drive, all the stuff we talked about, but it's at the Amazon server farm. That's what they call these things now. The data is stored there inside a cloud. Of course, that cloud is the internet. Okay? So on the internet, my data is stored. I can now access that cloud, that location in the cloud, from anywhere I can access the internet, which includes my phone, for instance. All the music I own, which is about 17,000 plus tracks right now, stored up here. On my phone, I have an app, a program, that connects to this cloud server via the internet, via the cloud, and it pulls down the zeros and ones from Amazon to my phone, and then interprets it on my phone as music, and plays the music on my phone. What a great thing. Now I don't have to, it used to be if I wanted to have mobile music, and I bought the first iPod the day it was available. I was in Japan at the time, but it's just, I love music and I like being mobile like that. I had, the cassette Walkman, I had everything. So, and it becomes a pain because I have more music than I could put on an iPod. So I had to start choosing what I put in the iPod. And then when you get new music, I want that music, not the old stuff, and you got to then reinitialize the iPod, and it takes hours sometimes. Anyhow, I don't have to worry about that now. Every piece of music I have is up here in the cloud. Well, if you take that a step further, say there's payroll information, and now you can do a backup, let's say, to the cloud. And Dell is getting in this business. IBM is getting in this business. Yahoo is getting in this business of backup services. And now you can back up your data in the cloud. When you hear cloud, you think of internet. Now you have your disk drives in your server room where you run your payroll. But if there was an explosion or there was a fire and your disk drives were destroyed, you can just plug in another computer somewhere else, and your payroll is up here in the cloud. And you just plug in a computer, download it, install the software, and your payroll is up and running. Great stuff. Great stuff. And all this stuff in technology we talked about, and the stuff we're going to talk about here in a minute, it becomes obsolete if we start going to this cloud. What are the drawbacks? Well, a lot of people are uncomfortable with their payroll data on someone else's hardware, as you can imagine. So the service provided by Amazon, Dell, IBM, has to be really good, and they have to prove to you that it's secure, encrypted, and so forth and so on. So you have to rely on that, and that's happening. At first, people were very reticent to do it. Now, it's not a problem. A lot of people are doing it because they're starting to realize that their business model for Amazon is based on the idea that they protect your data. So they back up your backup. So if their computer goes down, they can give you another copy. They take care of all that stuff, and they make sure you're the only one that has access to it. Occasionally you hear about somebody getting hacked and somebody pulling account numbers off it. It happens. But that can happen on your server in your closet too. So most companies, especially small, mid-sized companies, don't have the skill set to secure their servers, and they don't want to buy all the hardware and software and all the backups, so they just buy a service that runs in the background and updates their data, backs up their data constantly into the cloud. So they no longer have to worry about it. It used to be you had to do a backup, take it off-site, put it in a bank or something, and you had to do it daily. There's always a run to take the disk or the tape to the bank or something. Don't have to do that anymore. It's all happening, and especially for small, like I said, mid-sized companies that don't want to spend the money or hire the expertise. It's a growing area, and you're going to see more and more of it. I also have a backup service that does just that. It runs in the background on my PC, and everything I add or delete or change gets backed up as well. If I lose my computer, I can plug in another computer and download all my data and get up and running almost immediately. So I'm already doing that. As you can imagine, it's just going to grow. And all this talk of, I need more disk storage, I need more, you're not going to need more. You're going to start pulling it off the cloud. What are the downsides? One is security. Another, in a sense, is expense, but another is convenience. Convenience. It took a week or 10 days of constant running to get my music up there the first time. Which means if I lost my computer and wanted to restore it, it would take 7 to 10 days again. So it's slow. It's certainly easy, but it's very slow and inconvenient in a sense. If I had an external disk drive and I lost my music, I could plug it into a new computer, I'm up and running. You get the idea. The cloud has some drawbacks, but as the bandwidth of the internet gets quicker, you're going to find this becomes less of an issue. And you're going to see more of it than ever. So that's the cloud. And you can see here that Microsoft Web Apps uses the cloud to store your documents. Google Docs, there's a chart here. Here's some of the storage providers. If you want to look at these things, the one I use isn't even on here. And I can't think of it right now. But you can check out any of these. Flickr, of course, is mainly geared for photos, but it stores your photo. Oh, that's what it says here, sorry. Photos. You know, YouTube, if you think about it, that's a cloud. You're putting your videos up there for everyone else to share, and so forth. You can store photos and other things on Facebook. Google Docs, same thing as Office Web. You can take documents, store them up there, and then other people can retrieve them elsewhere. So you can see the advantages of all this. And there's Amazon, which I mentioned. Amazon is who serves up all the Netflix movies. Amazon's cloud storage and servers are what Netflix uses. Incredible thing to think about. But Amazon's learning a lot from that, and they started their own streaming service based on that. So the cloud storage, these are the positives. I can put my documents up there and someone else can pull them down from elsewhere. You don't have to use email, you don't have to use anything else, it just happens. Large files instantaneously, well I don't know about instantaneously, but it happens automatically. Other people can access it, you get the idea. So that's the future, cloud storage. So a lot of what we talk about here is going to become obsolete, in my opinion. For instance, optical discs. CDs, DVDs, Blu-ray. Well, these days are numbered for these devices. Why would I want one of these when I can buy cheap storage? I can digitize my movies. I can buy movies digitally now. You can pay for it, and then you have a library, for instance, on Amazon. I buy a movie, and it sits up there, and I can watch that movie from anywhere. I bought The Hobbit when it came out, for instance. That's how I watched it. And it's high def. It's not 3D, but it's high def. And I can allow my kids access by giving them the password and the user ID, or I can watch it from anywhere if I want to see it. So why buy this physical device? It's obsolete and it takes up room in your house. You know, most of us don't buy CDs anymore. Well, a lot of us do, or they wouldn't be out there, but a lot of us are downloading our music. We're not buying CDs. Real quick. CDs, DVDs, Blu-ray, all use lasers. And they shine a light, and then it senses a 0 or a 1, okay? I want to show you this website real quick. I say that a lot, don't I, real quick? And then it's not quick. Anyhow, here's a great picture of what's going on here. And the reason Blu-ray is so much better. Well, the original CD, which is still available, they have to put the data on the bottom here because the focus point is way down there. And they have to do that because it's the only way they can do the technology because of the shape and the laser itself. Well, better technology allows you to move it up. So a DVD, And also, what's different is the technology here, partially. The actual layered plastic and so forth that's in there. And they can put the image a little, or the data, I should say, not the image, a little up in the middle there. So now you have a little different aperture or size of the lens, and that allows you to get things closer. With a Blu-ray, they put the data right on top. And that does, and you notice this is different. The stuff, the plastic they use, allows them to do this. If you do that, what often happened with DVDs and CDs is the disc could tilt a little or your drive could get off a little. Well, with this, it's so close and it's on the surface, it doesn't matter quite as much. So you can store more data and you can retrieve it faster, so you have much more information. There's more information on a DVD than a CD, and the blue disc has the most information. So there's a quick run through on that, just so you get an idea. Notice the color of the light is different, blue. So the wavelength is a little different, which also makes a difference here in the media. And there's two lenses here also. So it has to do with the substance and then the actual laser itself. And this works kind of the same way a disk drive does, except notice this. It's one continuous track. The disk was rings. These optical disks are one continuous track, which is why it's difficult to rewrite them. But some of the technology allows you to do that. Okay. Don't put them in the sun. I'm not going to go over this. You can put your data on a disk. Okay, great. 100 gig on a Blu-ray. I think a DVD holds 4.5 gig, something like that. What a difference. So now you can get different tracks of sound, get different, a lot more data on there. So number one, you can put high def on there. You can put more subtitles, different languages. You can put more extras, all kinds of things. Okay, tape, magnetic tape. Some people still use it, but it's mostly a thing of the past, microfilm, and I'm not going to, let's just move on here. That's a backup drive. And some people still use these because they run at night, and every night your stuff goes on a cassette, which then somebody takes and puts in a bank or at home or something, so your data is off-site. But you know, if you have cloud storage, why would you do tape? And smart cards, we talked about those, I think, when we talked about output and input and so forth. And I've already talked about microfilm. Okay. This is kind of interesting, however. The lifespan. Your hard drive, magnetic disk, they're guaranteed 3 to 5 years. That's it for your hard drive. Remember, it's turning incredibly fast, almost constantly if you leave it on, although they will go to sleep. But and the moving parts of the head, it's just jabbering constantly. So that it's going to break. Eventually it'll break. Potential, of course, is 20 to 30 years. Nobody guarantees that. Your CD, DVD, blue disc, 50 to 100 years. Still only 5 to 10 years guaranteed. And 50 years for the solid state. Microfilm, okay, it's a long time, but who wants to use that because you can't access it digitally. Okay. Well, this is a server farm, a storage farm. It's actually becoming an environmental issue. These server farms are so big, they're so hot, and they have to be cooled, and the energy just to run them, and then the energy to run the coolers. It's actually a big issue, and they're trying to focus on this because it could make a huge difference since there's so much going on out there. Imagine how much storage just Netflix has to have every one of their users be able to watch a movie. What if 2,000 of them are watching the same movie? You got to have more than one copy, or you got to stream it. There's a lot of things going on there. But this allows you to store information that may not be day-to-day and so forth. Okay, here's the summary. You can take a look at that. Again, decide what you need based on your needs. Which type of storage you need based on your needs. Okay, storage, ASCII. We have a code set, Unicode. We store everything in zeros and ones, okay? And the idea is we need to decide how much we need. We have faster technology. Eventually, hard disk drives are going to go away. They're still cheaper, but they're much slower. They break more often. Eventually, they're going to be replaced, and they'll be a thing of the past. You'll be doing solid-state storage as well as RAM storage. And it's coming soon, because the more we use it, the cheaper it gets to produce, and the more the research continues to allow us to store more in less, for less money. So that's the future of storage, but storage is the key. And remember, cloud storage means geography and location means nothing. Okay, thanks. I'm done.